Institute of Structural Mechanics of Faculty of Civil Engineering for Brno University of Technology. First of all, I would like to introduce my colleagues which collaborate with me on this topic. Also from Institute of Structural Mechanics, Zbigniew Kershner, and his master student, Michal Bibina, who performed presented numerical studies in this work. And Barbara Kucharčíková is a colleague from the Institute of Building Testing. She performed fracture experiments, which I will present it today. Patrick Bayer is from Institute of Chemistry, and he deals with the microstructure measurement, which I will be presented. And the other colleagues are Lucia Malikova and Jan Klusak. They are from the Institute of Physics of Material from Academy of Sciences of the Czech Republic. So the topic of the presentation is modeling of interfacial transition zone and resistance to crack propagation in fine-grained cement-based composites. It should be difficult. Maybe it will be better. Some introduction. Cement-based composites belongs to the traditional materials which are used in the building industry. They are long-term using, but investigation of damage of elements made of such the materials are under static loading is still developing. This composite shows non-linear, more precisely quasi-brittle behavior. On the other hand, the individual components, it means the cement phase and aggregate, show very often brittle elastic behavior. These differences between behavior of the whole composite and individual components is caused by development of multiplied microcracking predominantly in the so-called interfacial transition zone ITZ. So, in the first part of presentation, I will talk about the fracture experiments and their evaluation, and the second part will be focused on the modeling on the effect of parameters of ITZ to the stress distribution in the interface between aggregate and matrix. So, about the experiments. For the study, we select two fine-grained cement-based composites. In the table, you can see the composition of these two composites. The composition was same in the amount of aggregate. In this case, of only the normalized sand, quartz sand, with maximum grain size of 2 millimeters, and the winner is the cement. The amount is the same in the both mixtures. The difference is in the water to cement ratio, and the second mixture contains also the super plasticizer admixture. You can see also the basic parameters of a fresh mixture is workability and bulk density of these materials. From this mixture, we prepare the specimens. The dimensions of the specimens was 60 by 80 millimeters in cross section and 1 meter in length. These specimens were primarily used for the measurement of length changes on the shrinkage measurements in these composites. After the shrinkage values was constant or not change so much, it was approximately after 90 days, we got from these specimens the specimens of dimension 40 by 40 by 160 millimeters is a typical beam specimens which are used for fracture testing of fine-grained composites. These specimens were provided before testing by central edge notch with notch that approximately about 1/3 of the width of specimens. This notch was in the center of the span, and span length was 120 millimeters. As I told, these specimens were performed the fracture test. It was a fracture test in 3-point bending configuration, and the tests were under the displacement control loading. It means we can record the load deflection diagram of these experiments, and these diagrams were evaluated from the first almost linear part of this diagram. We estimate a value of modulus elasticity, then using effective crack approach we determine effective fracture toughness, and using the work of fracture value we determine the fracture energy. In the table you can see the values of these parameters is the mean values and standard deviation of 6 specimens for each mixture. After the fracture tests were performed, we take the fracture surfaces of the specimens, and we perform the microscopic measurements to look on the microstructure of the materials, and mainly on the interface between matrix and aggregate. It was performed by scanning electron microscopy. You can see on the picture pictures for both materials. It's by detection of secondary electrons, and the magnification is 5,000 times. You can see the quartz sands is the aggregate, and then you can see the interface. You can see the basics minerals which are in this area around the aggregate. It's attenuated, port-planted, and as CSH gel. So something about interfacial transition zone. We focus on this part between aggregate and matrix. And on the left picture, you can see some picture from literature. There is the aggregate, there is the sun zone, the interfacial zone, and then this the cement matrix, then cement matrix. So we are focused on this part, the part between the aggregate and the matrix. So the other advantage of the microstructure measurement is that we can measure the distances of also in the 2D, but we can use it. You can see on this picture, I hope. This is the grain of aggregate. It's some larger grain of aggregate, and because it's not so easy to define the constant thickness of the ITZ, because as you can see of the micrographs, there are the different structures around the grain, and it's not so ideal as in this picture. There is the constant thickness of ITZ. So we decide to take into our modeling the thickness of ITZ as the distance between the big grain and to other smaller grains, and we measured in some points around the grain and take into account the mean value of this measurement. It means the for first composite we consider the thickness of ITZ 55 micrometers, and for another one 40 micrometers. So now something about the modeling of interface between matrix, ITZ and aggregate. It was performed by software ANSYS. It was made a simplified 2D model which which goes from the three-point bending geometry. In this geometry was tested our specimen, and the crack tip is on the interface between matrix and ITZ. It means when we loaded the specimen, the cracks grows from the initial notch, goes to the matrix, and we model the interface between matrix and ITZ. So the materials were considered as linear, elastic, and isotropic. Were defined by their elastic constant, Young's modulus, and Poisson ratio. As I told you, the thickness of ITZ was taken into account from the microscopic measurements. The modulus of elasticity of matrix was taken from the fracture experiments which we performed, and modulus of elasticity of ITZ were determined using so-called generalized self-consistent scheme. It was taken by half of modulus elasticity of matrix. Modulus elasticity of aggregate was taken from literature for the Ward sign, and also the Poisson ratios for materials were taken from the literature. We also did some parametric study. We considered the change of the matrix modulus of elasticity. We take mean value and 5% and 95% quantile. Which parameter we monitor? For quantitative description of influence of ITZ to stress state in crack tip vicinity, we evaluated opening stresses. It was a mean value of opening stress and the stress range determining according formula. And then we look on the critical applied stress, which were evaluated by means of critical value of mean opening stress. The first formula is for critical value of mean opening stress, and from this we calculated the critical applied stress. It determines the magnitude of applied stress under which the crack will propagate through ITZ. For this estimation of this parameter, we considered the fracture toughness 0.5 megapascal per meter. Square. Yeah. And because the is a typical value for matrix, cement matrix, typical value of fracture toughness for cement matrix. So there are some results of our study. There is a distribution of opening stress between interface through the ITZ and aggregate. The dashed lines are the interface between these two phases. For first composite is 55 micrometers, the thickness of ITZ for second is 40 micrometers. So, as I told you, we monitor the following parameters. There are for both composites in the table. The uppers are for the first, and the lower part are for the second composites. Both are the mean values of matrix. As I told, we calculated the parametric change of the matrix modulus of elasticity. There are the values of critical applied stress independent on elasticity of modulus of ITZ. it, I don't know how to say it, I forgot. When we have the biggest value of modulus of elasticity, the crack propagate more. It will be better to go to summary. Evaluation about summary. We evaluate influence of ITZ on stress distribution in cracked specimen. Crack tip was located at the interface between matrix and ITZ. We evaluated influence of various ITZ thicknesses and various elastic moduli of ITZ on the near-crack tip stress field was, and also the critical applied stress was evaluated. So now I would like to tell something about our future work or why we do this. There are some experiments we perform. I don't know, it's a good, you can see good. There are the specimens from fracture experiment. Now we take, we choose the second mixture. It was the mixture with plasticizer, and we put maybe here is there is the initial notch, and under the initial notch there is the inclusion. One inclusion, it's 80 by 8 millimeters along all width of all thickness of specimen, and we now focus on crack propagation along this individual inclusion. This experiment was performed with a steel inclusion because we would like to know behavior, and the difference between modulus elasticity value of steel and concrete is high. And last week there also you can see the fracture experiment after the fracture test. You can see the fracture surfaces, and here there are prepared molds with inclusions. Now the inclusions are from the rocks. It's a typical material for aggregate to the concrete. So now we have granite, marble, amphibolite, and basalt. On the data you can see, I think, basalt. So now we wanted to model this type of inclusion, and we know the parameters of these materials from our colleagues from Institute of Geonics. So we know the modulus elasticity of this material and also fracture toughnesses. So it's our future work. So thank you for your attention.